So, welcome to Epidemic, the summit. It's a great pleasure to be here. I'm Cristina Piazza. I'm professor for healthcare and rehabilitation robotics at the Technical University of Munich. And I will open this big day with amazing talks and great presentations. So we will start with the first session about the next generation robots. If we think about 20, 30 years ago, the scenario was with a robot confined in a cage, very far from humans. We see robots as dangerous for humans. Nowadays, in 20 years, with the amazing work that researchers and industry together have done, we can see that robots are becoming an integral part of our life. So we can see robot as becoming part of our homes or our living environment, our everyday life activities, and are collaborating and helping humans in, for example, work environments. So today we will have, for this first session, for international speakers that will guide us through different applications. So we will see how robotics made an impact, for example, in the field of healthcare, in the industrial application for grasping and manipulation tasks, for human-robot interaction, or even for rehabilitation purpose. And also, we will find out what are the technologies that enable this change in our scenario, in our view. And most important, the question is, what is the next generation? So, what is next? What are the new perspective and the new technologies and the future direction for robotic system? So, I would like to invite Professor Cecilia Laschi, our first speaker. It's a great pleasure to have her here. She's from the University of Singapore. She's also from the Biomedical Institute, Scuola Superiore Sant'Anna, and she's a pioneer in the field of soft robotics. And today she will present her findings and her research about how soft robots are changing and having an impact in human-robot interaction and in our society and everyday life environment.
Very much. Thank you. So thank you very much for the introduction to the session. Very nice introduction to my talk. We are used to machines that do a lot of things for us, and sometimes also they defeat us. And this was quite a piece of news a few years ago about the IBM AlphaGo defeating the Go Master. But this is not really new. The older roboticists here know about this one. That was really big news in the 90s already when IBM Deep Blue defeated the chess champion, Kasparov. And if you read from a newspaper of the time, you see that the reason why the machine was so strong is that it could examine an average of 200 million positions per second. So you see that it's clear why machines can defeat human beings. Human brains cannot do that. But when I looked for the pictures of this match, I always found something like this. So I couldn't understand why there was a person there. So I thought it was the wrong match, but there was the blue written there. And then I realized, and you probably know why the person is there. The roboticist is here. You know, yes. For this, right? Just for moving the pieces on the chessboard. So this is robotic. Robotics is about this, about the movement. In robotics, the intelligence is not thinking of the chess moves, but it is also how to move the pieces on the chessboard. So a more interesting challenge in robotics is actually soccer, because there is a lot of sensory motor coordination involved here. And there is actually a challenge going on, the RoboCup, that was launched in 1997. And I mean, it says that by middle of the 21st century, or our century, there will be a team of human robots playing soccer against the winner of the World Cup. So how far are we from there? If you have seen some videos, we're not yet very competitive with robots. And if you ask roboticists, you say, okay, but they are complex. These humanoids, because there are many sensors, many actuators, so the control is complex, sensor motor coordination is complex, but I'm asking rather if they're too simple, because they are way simpler than any living beings. So why not learning from nature? What we observe in living beings is that they are complex. They are way more complex than any of our robots. They operate in a complex environment, not the structured environments of robotics, but still you observe a very smooth, efficient, fast behavior. So a complex system, complex environment, but a fast and efficient behavior. So there must be some simplifying principles somewhere, right? And this is actually what nature does, so to simplify when they work. Not the way they are built. Embodied intelligence is one very powerful of these simplifying principles. It says that, in a nutshell, that the body has a role in controlling the motor behavior. So it's not the way the humanoid on the right here does, because the humanoid can perceive the step and compute a different trajectory for the leg, for the feet, but the dog in the center does it differently because it has compliant joints, and it can just negotiate small obstacles, small steps by the mechanics of the joints, with no involvement of the nervous system, no involvement of computation. So you see this is very powerful, and according to embodied intelligence, the behavior emerges from the interaction of the body with the environment, of course, in a specific task. So, okay, we can simplify our robotics tasks, our control tasks, if we consider embodied intelligence, but we need to consider these interactions. Our robot has to be built in a way that these interactions are used. So we need a compliant body, soft body. This is what actually motivated soft robotics, which is in fact very much about deformations. So it's the use of soft materials, but it is also the use of compliant structures in robotics. This is a wonderful model for me, an excellent model for soft robotics. It's quite clear, because it's an animal with a completely soft body, but it is also an excellent model for embodied intelligence. I would not go too much into the details. I love this animal and this movement, this reaching movement. You see there are so many muscles involved. This arm has an infinite number of degrees of freedom, can bend in any direction, any point of the arm. So in robotics terms, it is a nightmare. But if you look into the biology, you find that the brain has only to set 3 control parameters. So it's a huge simplification mechanism, and the simplification is given by the interaction with the water. So it's the water itself doing a good part of the job here. But so we did experiments that I'm not showing, but it depends on being soft, on being in water. The octopus cannot do the same amount of water. Passive parts, the distal part, and so on. So I hope I convinced you. We found that the trick is in the muscular structure of the octopus arm that we try to reproduce basically in a nutshell. It's heavy longitudinal and transverse contractions that we try to simulate here, and we also built a full octopus robot out of that, but what is important, this is just to verify our principle, but it's only when the principle is abstracted into a mathematical description that we can use it for engineering, that it becomes engineering, because you can use the mathematical model for designing your robot. And if you want to capture embodied intelligence, you have to model not only the deformations of the body given by the actuators, I call them internal interactions here. This is very common. This is what we do in robotics, right? And also in soft robotics, there are some modeling techniques to correlate the actuators' action with the deformations of the body. But to really capture embodied intelligence, we also especially need to model the external interactions, either with solids or fluids. Of course, with the octopus, we were interested in modeling the fluid interaction because there are these interesting swimming behaviors in the animals that we could reproduce. This model that you see here actually coupled and integrates the models of the deformations given by the actuator, so this pulse contraction of the mantle, with a model of the fluid dynamics involved. And you see how the model can describe the behavior of our prototype quite nicely. The interactions with solid surface are very relevant in robotics because locomotion is about that. So we have models of leg locomotion, for example, in robotics, like the sleep model, which is widely used. In our group, we learned from the octopus how we can walk underwater with sort of legs, because they use their arms as legs. And we added some parameters to the sleep model, so it became the U-sleep, underwater sleep. And you see that many things change, like what is very evident is that the angle of attack is different. And you see that the gait pattern is sort of hopping. But what we found very interestingly is that there are self-stabilizing gaits. And this is very much in line with the hypothesis of embodied intelligence. So having these self-stabilizing gaits allows to reduce the energy need a lot. And you see here that the robot can also keep session very nicely and with very low energy need, basically no energy consumption. So once we have the model, we can design our robot for some purpose. In this case, the purpose is to take samples of sediments to look for microplastics. And you see that the control is very, very simple. There is no coordination of legs, but legs are compliant. We implement the U-sleep in this robot, and it can walk with very, very low energy consumption and can negotiate small objects with no involvement of computation. There are other many possible applications for soft robots. Some of them are in the biomedical field, so going from endoscopes that you want to be soft to navigate inside the human body, but stiffen when doing operations. This is also something learned from octopuses because their arms are soft but can stiffen very much. Rehabilitation, assistive robotics, up to artificial organs. So, soft robotics is contributing to the growth of the robotics market. It is part of it. You find many of this kind of forecasts if you Google a little bit. So I just took one from one of the companies I find reliable, but you may find different numbers. But that's not the point. The point is that you always find this trend. And so it seems that this market is booming. So is it going to contribute to this also? So if this robotics market is booming now, is it the right time to consider this possible effect that was not considered when the phone and smartphones market started? So I think that soft robots contributes to a different vision for future robots. I use the word sustainability to sum up everything, but there are really different aspects inside this word. So of course, one is the energetic and environmental sustainability. So, of course, rethinking the materials that we use for building robots can help us thinking of materials that are reusable, recyclable, even biodegradable. So we can think of robots with a life cycle, like natural living beings. So they are born somehow, grow, evolve, and then when they die, when their life cycle is finished, they can biodegrade and integrate back in the environment. I think that being computationally efficient, like with embodied intelligence, is a very key step to reduce energy need and to use energy harvesting techniques with small amount of energy. Of course, we have to work on the technical sustainability. Robots must be usable, so they should be able to learn themselves, to learn new tasks, to modify their own body to do different tasks, and also learn how to interact with human beings. And of course, there are a number of non-technical issues still related to sustainability, economic, first of all, legal, social and ethical. For example, in my opinion, it is very key to think of new economic models that can consider the work that machines can do and make use of that instead of just considering that a threat for the society, as well as we have to think of these social models in advance. What kind of interaction do we want to have with robots, and then design robots accordingly, and not the other way around, which is very much technology-driven, which is what is going on today with technology. So for me, the right question is not what robots will do in the future. This is the typical question we receive, there's robotics, but we should reverse it and ask ourselves, what is the role that we want for human beings in the future? What kind of jobs, what kind of activities, what kind of engagement? And then we, as roboticists, we should design and develop robots accordingly to that. So, let's go back to this. Let's have a robot moving the chess pieces and having a person thinking about the moves. This is a robot helping, I'm sorry, I don't know. Helping a disabled person to play chess, Chinese chess with a friend. And we need this, we need robots in so many jobs that actually we consider inhumane. So they are for robots, they are not for human beings. Not only in developing countries, even in our industrialized countries, there are jobs that are done by human beings just because robots are not good enough yet. Like cleaning tanks, or operating in rescue. So let me pass to the good news. We're strong in robotics. Of course, this is the number of scientific publications, so it is science, it is research, and you see, of course, United States is top. But if you sum up the European countries, I'm just summing up those few that appears in the top 10, 11, you see that we are already over the top one. And we also strong in industry. We know that traditionally, especially Germany and also Italy, is strong in industrial robotics, but even in service robotics, as it's shown here, the number of suppliers is very high in Europe, not only in established companies, but even in startups. And so let me conclude what this scenario can bring us so robots are coming, and we should decide in advance how we want them to be and to behave. Europe and Germany are strong in robotics, not only in research but also in industry, and Europe can be leader in this sustainable progress of robotics, because we have also here in Europe a background which is grounded in humanities, social science, so we can couple with those aspects as well and nurture the new generation of robotics engineers. And actually, robotics can be the leverage for Europe to be competitive in AI internationally. So for me, robotics is actually something that can give value to Europe, can keep the competitiveness of its industry, support economic growth, and in the end, ultimately increase jobs. Okay, so I thank you. I just leave with this joke. Don't let humans take robots' jobs. Thank you. Sorry, ho sforato un pochino, scusa.
Thank you so much, Professor Cecilia Laschi, for this very inspiring presentation. Now, if we have questions from the audience, please raise your hand and feel free to ask. Maybe we have a microphone. Thank you.
Hi, thank you. It was great. Can you tell us maybe about something particular that you are researching right now, like working on a, I don't know, kind of a production plan of soft robotics?
Yeah, now I moved to Singapore, as you see from our affiliation, and there is a strong focus on elder care, because population is, of course, aging, like in Europe, like here. And so there are investments to help, I mean, to build robots that can help in elder care. So that's what I'm now doing that. So you have seen the shower robot in my videos. That was a European project. So I'm going on along that line, trying to identify the needs in elder care for robots. So again, I'm starting this with a user-oriented approach. I see, because in Singapore, technology is very advanced, robotics is very advanced. It is used in the city. You find robots, and you find robots even in a hospital. But I think that it's a little bit technology-driven. So in robotics, we are strong in building this kind of robots. For example, navigation is very strong, very robust. So we have a robot that can navigate inside the hospital. What can we do? This is the kind of approach that I think they're using, which I don't like. So what I would like to see is that, okay, this task is very difficult for some reason for the nurses, or it is dangerous, or it is I don't know what. And then can you build a robot that can do that? That's much more interesting in my opinion. And this is what I'm currently doing. Thank you.
Thank you for the presentation. Do you see the application of soft robots, for example, in elderly care or other industries in the near future?
Yeah, definitely so. So, of course, I'm starting from the needs of the elderly and the nurses and caregivers, but of course, in my mind, I have a soft robot around them. So what I think I can add with the soft robot is a more physical interaction, and more physical to be more natural. For the user, for the caregivers, so it can even be an interface itself. So if I can touch the robot and show the robot the position where the object to grasp is, it's much more natural than using any other interface. And again, I want to take care of the allocation of roles. So again, the robot should do the physical work, but I would like that the real care is given by a human person, you know. So
we have time for one quick question. I have one. So what is the role of the anthropomorphic shape, in your opinion? Because you show very bio-inspired design.
No, thanks for the question, because yes, my research is basically bio-inspired, but what I always say is that a bio-inspired robot is not a robot that has a similar shape. So when I say that I want to abstract the principle into a mathematical model and use it for designing a robot, then for me that robot is bio-inspired, because it embeds the principle that I learned from nature. But the shape, I don't want the shape to be similar. I mean, it can be, but even if it is not, that's fine, as far as I embedding the principle inside my design. Instead, I see many claims of my inspiration just because the shape is more or less similar to some living beings, which I don't consider really my inspiration. So thanks for the question.
Thank you so much again, Professor Cecilia Laschi. So we move to our next speaker, Professor Ferdinando Rodriguez. He's professor for medical robotics at Imperial College London. He's the pioneer, is conducting research on the field of surgical robotics and will present his results and the results of the Handling Center on this topic. Thank you so much.
Thank you for having me. I'm very happy to contribute to this incredible initiative from Munich, from Sami and the team here. It's been a pleasure to be here. I wish I had been here for a little longer, but in the interest of time, I'm gonna shoot off. As Christina said, I am professor of medical robotics in Imperial College, but I'm also the co-director of the Handling Center. Now, the Handling Center is a fairly large initiative. It's a research hub. It is a place for translational teaching, and it is a place where you can pump prime and bring some of the technologies from bed to bedside, from bench indeed, from bed to bedside with a very short hop, from bench to bedside. And of course, it comprises research from a number of academics, so I will not, over the next 15 minutes, have a chance to go through it all. Needless to say, it has 4 pillars. We work around robotics, sensing and imaging, and of course, a significant focus on global health and affordable robotics. Now, within the context of the Handling Center, which I co-direct with Aradasi, who's the clinical co-director, I also run my own research group, which is called Mechatronics in Medicine. That was set up in the 90s, and the focus has always been predominantly on hardware, but certainly on both. So mechatronics, a system for the benefit of healthcare, in diagnostics, in therapy, sort of surgery being one of the top priorities. Now, in the context of surgical robotics, and that's basically the starting point, we were among the first, with a few other selected centers across the globe, in looking at ways to make these robots in surgery a little bit smarter, because, as some of you may know, they are among the dumbest. Yeah, because you want to make the systems as safe as possible, because they were the systems that were used outside a cage in close proximity to an anesthetized patient and the surgeon. And so it took us a very, very long while to try to figure out smart ways to get these robots to interact a little bit more cleverly with the world. Now, cooperative control, which we called hands-on robotics, and it was called virtual fixtures by many others, still took this idea that surgeon and robots worked together in pursuit of better outcomes. And this is a very dated video that I still like very much, because it captures what cooperative control meant in the early 2000s. So the robot is holding a drill. The drill is also held by the surgeon, and the surgeon and the robot work to cut or to mill away a part of a bone to place an implant within it. So within a safe region, the surgeon is controlling the tool. At the boundaries of that region, the robot motors engage, preventing you from doing something you shouldn't. Now, this particular system has gone through a long and perilous journey from bench to bedside, and I think at least the essence of it is in the current robot marketed by Stryker, which is called Mako. But it is definitely the case that even though this type of tech has been out and about for almost 20 years, and in many ways it is rather mature, there are not so many of these robots in the operating theater today. And I think the reasons are multiple. Some are ethical, some are clinical. Is there real functional benefit to the patient to the employment of these million-pound devices? And some are technological. And because, of course, I'm an engineer, some of the focus of the research that I've carried out in first person has very much to do with improving technology for better, more effective assistance in surgery. And having gone through many, many iterations of this vision, I still believe that, or at the moment I believe that the sort of advancement that are going to come our way in the next sort of 5 to 10 years revolve around these 3 main concepts. The idea of smooth interaction, so delivering the right information at the right time in the most seamless way possible. Automatic recognition, which anyone who's seen a surgical robot will understand as being a big challenge today, and that is that if you want to wheel a surgical robot in the operating theater, there is a lengthy setup time, an enormous amount of deviation from your clinical surgical workflow that obviously makes the deployment of tech in this space very complicated. So if we could make that integration more seamless, it would certainly have advantages. And finally, the robots today across the board, and we're talking from Da Vinci to Mako Striker, they are incredibly bulky, they are quite expensive, and they basically do not fit the blueprint of an OR, which, for those of you who have seen one, is an incredibly cluttered, unsafe, and complicated environment with sterile, non-sterile interfaces, human being all over the place, and very, very little empty footprint for the robot to be wheeled in. So new devices that are smaller, more compliant, soft robotics being one of the big challenges to deploy in surgery is one of them. So over the next sort of 5 to 10 minutes, I just wanted to give you a glimpse as to some of the things that we're doing in the Hamlin Center and the Mechatronics in Medicine Lab that I think promise better effectiveness of this surgical system in the not-too-distant future. Now, if we take the example of this robot, this is a robot by a company called Smith & Nephew, and it is the most compact version of a surgical drill. What you have, well, in this case, is a tool, but the drill, I just cut it out in the interest of time. Point is, it highlights some of the complexities of a surgical system today. And importantly, I highlight the idea that you have a screen, and you've got these very intrusive percutaneous markers that help you to track a limb during surgery. Now, everyone here, because we're all roboticists or machine learning scientists, we know that in order to provide a system, we must know where things are. And things can be located in space through any form of registration, but of course, they must be tracked. And as of today, commercial systems now use these percutaneous fixations, which is basically, imagine them as screws that you pierce through the skin, through the screen and into the bone, that remain there for the duration of surgery. So clearly, very invasive, an additional stab wound, an additional incision, additional risk to the patient. And so these two things are, for the moment, the real focus of my group's attention. Can we get rid of the screen and all the difficulties that happen in triangulating what is a two-dimensional image with respect to a three-dimensional scenes, and can we make the whole process of tracking, for example, a limb, less intrusive and more better integrated within the clinical workflow? Now, with regards to better guidance, the absolute top technology coming our way in the not-too-distant future is undoubtedly augmented reality. This is some work that we're doing at the moment with the HoloLens 2, which some of you will know is the Microsoft offering of an augmented reality system. This is a system that allows you to overlay visual cues on the real scene in a sort of seamless, integrated way. Now, clearly, this machine is not good enough for prime time. It's not accurate, robust, or fast enough for clinical use, but it gives us a glimpse of the type of assistance that you could provide the surgeon in the not-too-distant future. So what you saw in the video on the bottom right-hand corner is my PhD student, in this case, Hisham, who just graduated with a PhD in this space, being able to register, machine, and interact with an exposed limb, which is obviously in this case is a plastic bone, with the visual guides, with visual cues about what is the next step in the procedure, directly augmented into the scene. In the case here, you've got a larger version on the right and the real bone on the left. But as you can see here, as in this case, the PhD student operates with the limb, you see this sort of color-coded display that allows you to know where you should be cutting the bone, and a small little arrow here that shows you directly on the exposed surface of the patient exactly where the precision should take place. Now, clearly, a much more intuitive approach to surgery and guidance than using a screen and having to triangulate between the two. I would say 5 years ago, we had nothing. 5 years later, we have this. So clearly, good alignment, centimeter accurate, with a refresh rate of about 5 to 8 hertz. We can certainly think of pushing forward with the hardware and the software such that in the next 5 to 10 years, this will probably be ready for prime time. In a similar way, this idea of automatic tracking, getting rid of those triplets and replacing them with some of the state-of-the-art technologies in this case, we've got depth sensing. So we know that at the moment, you've got these two camps with regards to the measurement of 3D scenes. You either have fast and sloppy or accurate and slow. And so in reality, surgery would want a compromise between the two. So you want millimeter accurate measurements in 3D, but you'd want it at several tens of hertz. And we're slowly but surely getting into this direction. Point is, though, through carefully tailored deep neural networks and the right amount of training, I'm going to run it again, that helps the machine to understand what is bone and what is not through a number of semi-automatically segmented scenes of real patients, of cadaveric patients, and of plastic bones. We're now able to look at a scene and interpret that that is bone and that is not in the presence of a number of complicated and unknown objects within the scene. And importantly, and you see it in this video here, we now are about 5 or 6 years down the line, able to manage partial occlusions and to abstract the performance of that network in identifying what is a feature within a complicated scene that is agnostic to the camera that you've trained the network on and the patient or the limb that you have deployed on. So in a sense, a very, very powerful glimpse into a future not so distant where you wheel a machine into the operating theater and the machine can look at the scene, look at the patient, and automatically and without any user input know in what way to guide the surgeon through the procedure. That is with regards to software, imaging, and information delivery. We are also doing quite a bit of work on devices. We really don't have time to go through any great detail, so I just wanted to give you a glimpse about some of the things that are a little bit further ahead. This is a large project, and it's an important one because it's still ongoing, and it is a partnership with Nasir Nawab and the group here in Munich, where we're looking at telemanipulation of endovascular catheters for a number of procedures. So the system, as I said, is master-slave, is pneumatic, is MRI compatible, and of course allows the clinician to work within the remit of, for example, fluoroscopy, so X-ray imaging, which could be quite damaging to the patient, to the surgeon, if, as they always do, they work in very close proximity to the radiation source. And of course, it is very well suited to the delivery and execution of this type of endovascular procedure within the bore of an MR scanner, which, as some of you may know, is actually quite short, quite small and narrow and long. So it is very difficult for the operator to work within the bore, so having technologies like this could really push everything a little bit forward. We're also working on a whole range of soft devices, both for actuation and sensing. This is a particularly interesting piece of work that is only possible because of the unique facilities we've got in the center for thermal fiber drawing, which is a technique which, a little bit differently from normal extrusion, allows you to start working from a preform, from a short and fat version of the fiber you want to create at the end. So you create a 3D prototype of something that is large and short, and then you very gently draw it, so you stretch it so that it becomes thin and long. And that particular technique allows us to develop fibers that I have not been able to achieve in any way, shape, or form, regardless of how many you throw at it, by any other means, including extrusion, which, as we know, is the main form of creating catheters for surgery. Now, what you see here is a prototype of a cochlear implant, but what is unique about it is that it's made of material which is a shape memory polymer. So a bit like nitinol, it is activated according to the temperature of its environment, and so it's designed to be spiral, which is the shape of the cochlea, and stretch straight at room temperature. So the idea is that through the careful insertion of this straight transducer through the cochlea, you can then have the transducer curl around the cochlea in this sort of semi-assisted way using robotics and augmented reality to try to make it a less invasive and less prone to damage in the inner surface of the cochlea itself. We have, yes, and then we'll finish off with my third child. Yeah, this is a project that has been in my research group for over a decade. It started as a proof of concept funded by the UK. It was then an ERC starting grant. It then became Eden 2020, which is this large consortium with TUM and TUM and a few other partners. And it's all about neurosurgical drug delivery and a platform for precision neurosurgery. Now, again, I will not go into the details of it, but it is very much a biologically inspired design where a number of segments make up the catheter, the interaction of which allows the catheter to be steered along three-dimensional trajectories within soft tissue. Now, what is advantageous here, it is that it is less intrusive, and as you can see here, you've got a number of working channels that can then be used to deploy any number of minimal invasive instruments. They could be used for diagnostics in situ using fiber optics. They could be used for laser ablation. They could be used for drug delivery. And in the not too distant future, they could be used for electrical stimulation and recording. So a nice broad platform that is now at a pre-commercial stage. So we've got a pre-commercial hardware and software with a medical-grade catheter that is sterile and ready and able to be deployed in vivo. We've run a number, in fact, of clinical trials on the ovine model in Italy, and now it's looking for the next journey. And you know, when we started Eden 4 years ago, I thought to myself, with all of this de-risking, certainly a Medtronic will just take it off me and run with it, because it is expensive technology, but we're not there yet. So whether this is spin-out, a follow-on project, or another means to take it from all the way from bench to bedside, yeah, your guess is as good as mine. So to conclude, I just wanted to end on a positive in this particular conference. I think we are going through an absolute technology revolution. It is the best time to be in our field I have ever seen. Yeah, the rate at which supportive and assistive technologies are coming to the rescue with deep learning network, GPU acceleration, and even the digitization of healthcare are allowing us to really dream big, so that maybe before I retire, yeah, we will not have this sort of percutaneous pins in the operating theater, and we'll have a bit more high tech. Yeah, very, very topical here, a bit more high tech in surgery. Thank you very much.
Thank you so much, Professor Rodriguez. If there are any questions from the audience?
Standing silence.
I have a question about the Project Eden. So you bought all of this medical grade hardware to de-risk it. So what are the actual challenges that you're facing?
It's predominantly, and I would say almost exclusively, the business case. Because unfortunately, neurosurgery is a niche market, especially complex neurosurgery. And so in reality, finding the right business plan that allows what will be a £1 million technology to be deployed and commercialized, which will be another few £1 million worth of CE marking and certification, that's the trick. So I think we've basically taken it all the way to the top of what even the most translational university research groups can do. Now it has to be spun out. But if it's a spin-out from a university, then you need enormous amount of investment. The sort of thing that happens in Taiwan and possibly in the US, but the European market is much more risk-averse. So they want low funding and very short horizon for return on the investment. And I think that makes spinning out technology like this very difficult.
Any other questions here in the front row?
For example, you were talking about the depth sensor in the knee surgery, and you mentioned that the OR environment is notoriously cluttered and uncontrolled. Yeah. So with lots of line of sight problems and so on and so forth. So how do you envision, for example, a sensor like a depth sensor being robust enough, reliable enough in the field?
So our best results came with using the HoloLens for image augmentation and a separate depth camera to do real-time feature identification. However, we did run a proof of concept on the HoloLens onboard sensors. You know that it has an RGBD sensor on board, which clearly is not designed for the type of brute forcing that we do, but it definitely was good enough to demonstrate that the principle of mounting the camera on the headset would clear a lot of that line of sight, because you always have to assume that the surgeon will be looking at the thing that they are operating on. And so if you mount it on the headset and then it is co-located, you can basically close the circle. The alternative would be to mount it on the tool, and as you look at the evolution of hardware, they're getting smaller and lighter, and so the idea of mounting it on an instrument is not so crazy anymore. Yeah? So you don't necessarily need a tripod for it. And those would be two ways in which it can happen. Right? Now, in the shorter term, it's a hybrid. Right? So, for example, depth sensing and optical tracking, which is what the standard of care requires.
Do we have other questions? maybe one quick question from the audience. Cecilia?
You also take some inspiration. You mentioned Biomimetic.
Yes.
So what's your inspiration from nature?
So the Eden 2020 was inspired by the ovipositor, so the egg-laying channel of certain insects. And the beautiful thing about 15 minutes and 12 years is that you can dissect all of the failures, miserable failures in copying nature, and just focus on the highlights. So even abstracting, as you very, very, very wisely said, the principles and then finding a way to make it work with the limits of engineering, manufacturing, was maybe a 5-year journey. But what you saw there was the evolution. So for example, the insect has barbs, backward pointing teeth on the outer surface of the ovipositor. We use surfacing content to be able to have some of that advantage because we cannot really make the topography that nature has done so cleverly. Yeah.
Okay, so thank you so much.
Wonderful. Thank you.
So I would like to invite our next speaker on stage, Professor Laura Marcel Crespo. She is professor at the Technical University of Delft, and she's conducting research on assistive device and rehabilitative device. Please come on stage, and we are looking forward to hear more about your research.
Thank you very much for the introduction. So let's just start this presentation with an imagination exercise. You wake up one morning after a long, sleepless night working on your projects, and when you get into the kitchen to get your first warm cup of coffee, you cannot reach for and grasp your cup. Your hand is weak, your arm is cramped, and you cannot open your fingers, even if you put all your mental effort into it. So this is the reality for more than half of the 15 million of stroke survivors every year. So think about it. 1 in 4 adults will suffer from a stroke in our lifetime. And a stroke results in cognitive and motor impairments that limits the ability of the patients to perform activities of daily living. It limits the independence of the patients and puts a tremendous financial burden on society. But luckily, our brain is capable of reorganizing its structure, allowing for the recovery of the lost function. The question is, how can we maximize this recovery? Neuroscience evidence tells us that patients should engage in high-intensity and task-specific training. But after many years interacting and observing therapists and patients in several hospitals around the world, I can tell you that this is not the usual care, because this kind of ideal training environment is too exhausting for the therapists. So as an engineer, I developed robots for rehabilitation, as for example here the arm-rehabilitation from Hokoma, one of the more successful exoskeletons for rehabilitations nowadays. And current robots support therapists in providing high-intensity training and also incorporate very motivating virtual reality games. But current robots suffer from important limitations. First, these robots only support the patient in performing the movement, and it's not providing the somatic feedback coming from the skin and from your muscles. And the somatic feedback is very important in order to successfully manipulate objects. Secondly, we have developed robots with many degrees of freedom, super sophisticated, that from the point of view of the engineers, those are fascinating. But from the point of view of the therapist and the patient who should use these robots, these are too complex to be employed. This limits the adoption of the technology into the clinical practice. And just as an example, only 30% of the robots that have been developed for rehabilitation have made it into the clinics. And from the engineering point of view, this is a very big failure. And finally, these very motivating virtual reality games only provide an abstract visualization of the movements of the patients that are performed in one place on a 2D screen somewhere else. And this abstract visualization is cognitively too demanding for more than 50% of the stroke subjects that also suffer from cognitive impairments. So training with an abstract visualization and without somatic feedback is far from being task-specific. All this results in current robots actually hampering the recovery of functional movements, such as, for example, grabbing that cup of coffee. But with the emergence of new technology, low-cost technology like head-mounted displays and actuators, a new horizon opens for rehabilitation robotics. So I'm personally fascinated with the possibility of exploiting neuroscience concepts, such as, for example, body ownership or psychophysics, in order to maximize the recovery of the patients. So together with my interdisciplinary group at TU Delft in the Netherlands and the University of Bern in Switzerland, we combine our expertise in robotics and virtual reality with neuroscience knowledge in order to develop hyper-realistic robotic systems that allows for task-specific training. So I guess that everybody agrees here that this is not the ideal training environment in order to learn how to swim, because you need to see and you need to feel the interaction with the water in order to master this important skill. So how can we expect that patients regain functional movements if we don't provide them with realistic visual and somatic feedback? So my team, together with my team, we aim at providing this ideal training environment by a series of scientific innovations. The first one is the use of head-mounted displays to provide a more naturalistic and realistic visualization of the virtual reality. So by providing the patients with a first-person perspective of an avatar that is moving in the same way and in the same place where they are moving, we show that we can improve the movement quality of the patients. And it actually results in much more motivating training compared to the typical 2D screens. And perhaps more interesting is the fact that when we asked the stroke patients and elderly people who were part of this experiment to rate the usability of the system, they rated the use of head-mounted displays are more usable than not the conventional 2D screens, even if this population is not used to high-tech. We also found that with the use of immersive virtual reality, we can feel that the avatar is part of our own body, what is called body ownership. And body ownership shared neural correlates in our brain with the motor system. And in a recent experiment, we showed that actually this neural coupling is functional. By enhancing the body ownership over the avatar, we can enhance the motor performance of our patients. But immersive virtual reality is not only a very powerful tool to provide realistic visualization, but also it can be used to trick the brain of the people. So our brain is very plastic and adaptive, and we can adapt to change in the appearance of our body very quickly. Such as, for example, when you spend many hours under the sun, you will really quickly adapt to the change of color in your skin. And we can exploit this adaptability by tricking the brain of our patients. So we ran this experiment where we create the illusion that the arm was made of stone by providing congruent haptic, visual, and haptic feedback. And what we found is that the strength of the illusion, so how high the participants rated the arm to be colder and heavier and stiffer, was related to a higher excitability of the motor areas in your brain, and this resulted in faster movements. Such as, for example, when you want to grab a carton of milk that you believe that it's full, but it's actually empty, what you do is overshooting. But we don't rely only on our visual and our eyes in order to successfully perform tasks. Imagine, for example, that you are carrying a tray with coffees around a very busy room. In order to successfully perform this task, you rely not only on your eyes, but all the sensory information that is coming from your skin and from your muscles. So the second innovation that we are bringing is the addition of this somatic feedback during the robotic rehabilitation. And we do this by providing haptic rendering of interaction with tangible virtual objects during the rehabilitation. And this is actually not a very easy task, because in order to provide a fine haptic rendering, the first thing that you have to do is to maximize the transparency of our heavily constructed exoskeletons. And at the same time, we need to minimize the amount of assistance that we are providing to the patient to try to prevent that the assistance affects the perception of the haptic rendering. So we achieve this by developing controllers such as disturbance observers and model predicted controllers. But the question still is, is actually this haptic rendering beneficial when you are relearning to perform a multi-joint arm movement while you are interacting with objects with complex dynamics? That's why we ran an experiment with 50 people, and we asked them to learn how to invert a pendulum and keep it inverted. And half of the people trained with the haptic rendering of the dynamics of the pendulum into the end effector, and half of them without any haptic rendering, only with the visual information. And what we found is that, indeed, having this haptic rendering enhances the motor learning. And not only the motor learning of this specific task, but also enhance the transfer of the acquired skills during training to different tasks, such as this inverting a pendulum with a shorter rod for different dynamics. And this is quite a finding, because this is what we are trying to do. We want to transfer the skills that are gained during the rehabilitation into the clinics to the activities of daily living at home. Most probably you realize that our robotic device here has quite a limitation, and is that all the interaction that is done with the virtual reality was done through a stick. And actually, you don't wear a stick and you touch things with it, but most of the activities of daily living involve the interaction of our hands with objects with complex dynamics, such as, for example, grabbing that cup of coffee. That, by the way, it has a very similar dynamics as a pendulum. So in order to complete our hyper-realistic robotic system training, we started our quest to design a new hand rehabilitation device that could be used to provide this fine haptic rendering to the hand. But we didn't want to avoid just designing another hand device that it's going to end up in a deadlock because it's too complex for the therapist to use. We engage in a clinical-driven process. And then, in order to do this, I equipped my students with a very important tool, that it's not actually a computer, it's not a robot, it's not a screwdriver. I equipped them with a white coat, and I sent them to spend several months into the clinics of our partners at Erasmus Medical Center and in the University Hospital in Bern. So during these months, they were shadowing the normal therapy that the therapists were providing to the patients every day. And all their observations were summarized in a journey map where the arm rehabilitation experience from the patient's point of view is shown. We also performed questionnaires with the clinical personnel, not only therapists, we included also nurses and also doctors in order to gather the clinical requirements for our hand device. And I can summarize this in 5 points. The first one is that they wanted a device that is not complex, that is easy to use. They want a device that it takes less than 5 minutes to put the person in it. They wanted a device that can be used by patients with different hand sizes. They wanted to have a device that is providing the haptic rendering. And they wanted a device that it's not complex, but it's able to provide physiological movements of the hand from full flexion to full extension. And after many iterations with the therapists, and that included fast prototyping and parameter optimization, I'm very proud to show you here the solution. This is Sprite. By changing this mobile part here, you can use the device with patients with different hand sizes because it optimally locates the metacarpal joint. Then it takes less than 5 minutes to secure the patient into the hand because they only have to slide the fist into a cylindrical form. Yeah, and in less than 1 minute, we are able to provide the full assistance in the full flexion and full extension. And of course, we developed the robot in a way that it has as transparency as possible, so it's able to provide very fine haptic rendering. So our hand device can be mounted on several different robotic devices, from the exoskeletons that I showed you before to the Lambda 3 here from First Dimension. And we combine our robotic devices with very motivating games. Those are quite addictive. And they incorporate gamification elements, but also the possibility of interacting with elements that have rich dynamics, such in this case in here. So although our clinical partners were very happy and, about our solutions, it was very highly accepted in our quest to design less complex designs that are inherently safe, that are portable. We designed a different one, and it's to be used in minimally supervised environments, such as, for example, the home of the patients. So this device here is also 1 degree of freedom robotic device that it's based on a deformable shell, and it's actuated only with 1 degree, with 1 motor. So it's very highly portable. And and it can very nicely render the interaction with different elements in the virtual environment, such as, for example, these liquid dispensers, where the liquid have different densities. So that was the talk. To recap, we are facing a very big health challenge that I believe that it can only be tackled with the convergence of the health and engineering fields. And robotics are leading societal transformation by providing this high-intensity training of our patients. But by including neuroscience knowledge, such as, for example, the use of immersive virtual reality and haptic rendering to provide realistic visual and somatic feedback, we could further boost this revolution. And with this, I conclude the presentation, and I will be very happy to answer your questions.
Thank you so much. Very interesting presentation to see how these new technologies are becoming part of the rehabilitation process. So do we have some questions from the audience?
Hi, thank you for a very nice presentation. So when you included haptics compared to the visual stimulus, so when a person is using only the visual stimulus, and in the other case you have a group which used visual stimulus plus haptics. So how much was the improvement?
Sorry, can you repeat the question? And it's difficult for me to...
When they used haptics, you mentioned there was improvement if they just look at the pictures, right? Mm-hmm. How much was the improvement compared to when you look at the two groups?
That's a good question. I think that it was actually more than twice better learning. But just to go more into this experiment, it was 2 times 2. We have the people working with haptics and without haptics, but also with assistance and without assistance. And the assistance was the compensation of the weight of the participant with the exoskeleton. So the enhancement of the motor learning of the inclusion of the haptic rendering was higher when there was not assistance. There was the assistant was hampering somehow, but still, assistance plus haptic rendering was better than assistance and no haptic rendering. So it really depends if you were also applying assistance or not assistance at the same time.
Any other questions? So maybe in the meantime, I have a question about the virtual reality environment you mentioned that you use for stroke patients or elder people. So what is the training time to get used to this environment for this kind of population? 0.
It was 0. It was quite amazing. So we also use augmented reality, as my colleague here, and with augmented reality it took more time. Because they need to get used to focus on 2 different places at the same time, the virtual and the real one. They have to do the switching, and it was complicated. But with the immersive virtual reality, with the head-mounted displays, was just right away. So, because if you think about it, it's more naturalistic, right? You are not doing any transformation. We are used to move the mouse and see the mouse moving on the screen. For us, it's very easy, but for patients, that's not easy. And just by showing an avatar that is moving as their own arm is the more natural thing possible, right?
Yes. Okay. Thank you so much, then, Albino, for the great presentation. So we move to our last speaker for this session, Professor Lucia Pallottino from the University of Pisa. It's a great pleasure to have you here, and she conducts research on distributed robotics, so how robots can coordinate and collaborate between them and with humans. Thanks, Lucia.
Thank you, Christina. Good morning to everyone. Yes, I'm working at the University of Pisa, and I mainly work on multi-robot systems. That is something different from the presentation you have seen until now, a very interesting presentation. So we will talk about society of robots. And as I mentioned, I come from Pisa. Pisa is a small town in the center of Italy where the Leaning Tower is, in a wonderful Piazza dei Miracoli, is a wonderful square, and it's a tiny city, and as in Munich, we usually go by bike around. So when I was doing my PhD, I was crossing to go to the engineering faculty, I was crossing the square, and had to take care of all the visitors. So I had to plan my motion with my bike to avoid people walking around and also taking the typical pictures that we do in Pisa. So it was static objects and also moving objects that I have to take care of, right? So I started working in motion planning. So how do we do replicate this kind of bad behavior that I had going by bike to robots? And so I started there. So one single robot has to move around and avoid objects and avoid obstacles, or moving objects or some external objects and static obstacles like walls. And that's where I started. But then I was working in a very nice environment where we had, in our lab in the Centro Piaggio at the University of Pisa, in the group of Professor Bicchi, we had a lot of robots doing a lot of different things. We had manipulators doing like uncutting the wrap around the pallets, or taking objects from a pallet and replacing them somewhere else. We had wearable robots like prostheses, like the soft hands. We did in collaboration with the Italian Institute of Technology in Genova, and our spin-off could be Robotics. So we have wearable robots, so robots that we wear on our body. And also, for example, here there is Antonio dancing with one of our robots that is a mobile base with an upper body that is anthropomorphic. So we have in our lab, but as you have seen now, until now, everywhere we have very different robots with very different kind of applications, and also with different kind of tasks and the implication of what they are doing. So I say, yes, okay, we do have nice, very nice single robots, not just in our lab, also outside. Here, for example, we have two examples. We have another spin-off that is doing mobile robots for cleaning in huge environments like hospitals or airports. Or in the right, we are part of the Euro team. There is another team here in Munich that participate to the Indie Autonomous Challenge. Here is a video on the challenge that took place last November in Indianapolis, and there was just one autonomous car, fully autonomous car, moving on a track to do the fast lap. Okay, so they were competing on the same track to do the best path. So we have also very advanced robots. So for example, this one is fully autonomous, high-speed robots, so high mobility. But those are single robots, right? But we cannot think that they will be like that forever. For example, the race, it's nice, but it's quite boring. The races are nice because we have competition. So we have seen also that around us, a lot of people, media, for example, are talking about robotics. Okay, robots are everywhere, also in our magazine that are not scientific, or in the media. And if you have a look at the numbers, and Cecilia already showed them, we have a trend. So those are different numbers, as she was mentioning. You will find very different numbers, but the trends are always the same. In the service robotic world, just for professional use, we do have a very high increasing numbers of robots in all the three typical sectors that are medical robotics, logistics, and field robotics. So we do have, and we will face, a large number of robots close to us, in our houses, while we work, in the hospitals, in the restaurants, everywhere. And those are other numbers to show you the increasing of the money that is going around in this world, and also the numbers of robots that will be sold in the future, now and in the future. So we will have a lot of robots around us. So it's not just the problem of having robots, single robots around us, but we will have many of them. So we have to take care of that. So we will face a society of robots, for sure, that are saying that. And when we have a society of robots, we have to take care of two different types of interaction. We have the one that we have seen until now, so the physical interaction between robots and humans. We will touch robots. We will get in contact with them. And this is a broad field of research that you have seen some of applications until now. But we will also have the robot-robot interaction. That can be physical, as in this video. Here we have our alter ego robot that is interacting physical with another one. They are, just to be correct, they are teleoperated robots at the moment, so they are able to stand up autonomously, but they interact with each other, friendly, hopefully, but they interact, and they are robots, so what do we mean with robot-robot interaction? What can we do with robot-robot interaction? So that's the questions I would like to not answer today, but to face today, because we don't still have a very good answer for that, because the problem is still open. But for sure, we will have to face this problem. And it's not just physical interaction, because the physical interaction, we can take care of respiration, the physical interaction, by the physical interaction of humans and robots that we already have some idea of, like soft robotics, for example. This is a soft robot. This robot has a soft actuation, okay? But what about the other interaction that they can have? So what we would like to see is something like that, for example. This is a human-human interaction without communication except for bad words, maybe, that they say to each other or scream. We don't know. But they don't really coordinate to each other. They don't have any rules, for example. They just go straight. Every human has his own goal, has to cross the crossing. And the team goal is to avoid collisions, right? The only thing that they want to avoid is collision. And they do that. Do you think we are able to do that with robots? No, absolutely not. We cannot do that with robots, not at the moment. But we still have to understand what is going on, which kind of interaction they have, how they coordinate. And we can see that in humans, but we have much nicer inspiration from birds or fish underwater. So we do have inspiration, and don't worry, we don't take inspiration by humans for that, so don't worry. Mainly from Italian drivers, don't worry. So the problem is how we can translate this kind of coordination in robots. How can we this is a very simple example of several robots moving around, avoiding each other, where they do this autonomously. There is no one controlling the whole system and telling the robot what to do. It's just the robot that interact with each other, in this case by communication, direct communication, and then they coordinate to avoid the obstacles, to avoid each other, and also to reach the goal. And for industrial application in this area, you can think about, for example, the warehouses of Amazon. You can see a lot of videos on the internet of these small orange robots moving around. They just move around in a kind of safe way, so they just go north, south, east, and west. And they're all the same. They're all the same in the same warehouse. They move like that, and they interact with each other. They are coordinated, and they can move the small objects around the warehouse. But the problem is that we have requirements for these systems. For example, in the Amazon system, everything is like pre-planned, but the robots are all the same. But we do have to face something different. As I mentioned before, we're talking about a large number of robots, and the robots are not done by the same company. They're not equal. We have legged robots, we are wheeled robots, we are drones, we are underwater robots. They will all live in more or less in the same environment. So we do have to ensure safety. For sure, that's the first requirement we have. They don't have to collide with people or the environment. They don't have to collide with each other, and that's the first keyword. That's correct. But we also want them to work together efficiently. So we know that we can put robots in the same room, and they will avoid each other, as they will avoid us, and that's okay. But it's not really coordination. It's not a good coordination, because they just avoid each other. They don't really collaborate in doing so. So we can, for example, for collision avoidance purposes. So we want them to collaborate to improve efficiency, not just to live safely in the environment, okay? And then that's another very important key one is heterogeneity. We want different robots to stay together. We do have a large community that is taking care of this, is of a larger number of robots, that is the swarm robotics community, but in there, the robots are all the same. Here, I'm talking about very different robots done by different company, but also able to move differently in the environment. So this is a very important keyword that we have to think about. For example, I buy few robots for my warehouse for a company, and then, for example, that they just deploy objects in the warehouse, okay? But then I have to buy robots that clean the ground, the floor of the warehouse. Maybe it's the company that sells me the forklift doesn't have the robots that clean the ground, so I have to buy another robot from another company, and they do not interact. They are not being designed to interact. Okay, so I'm forced to buy always and forever the forklift from the same company, but maybe I don't want to. I would like to have some kind of AGVs, as they call, autonomous guided vehicle from a company and other vehicles from another company, but then they will live in the same environment. So heterogeneity is really a challenge. Then we will have scalability, because today I will need like 50 robots in my company, and maybe in 15 years, and 10 years, I will have 70, 100 of them. I don't want to change the whole system to be able to handle and coordinate all these robots. So I would like the system to be scalable, easily scalable. And then we have security, and that is another very important word, because robots will communicate to each other wirelessly, because they are moving, okay? And there is a point of attack from external users, or a point of failure. So if I have a robot that is not communicating anymore because it's broken, is an object that is not acting and is not coordinating with the other. But I can have also attack on purpose, and I need the robots to be protected on that. So this is another important aspect that we have to face. So what do we mean with coordination? Coordination, we mean that we share resources, and those resources has to be shared in a fair way to improve the efficiency of the system, to make the system safe, and so on and so forth. So we have the communication network that is shared, so we have to take care about that. They communicate through the same network. They may communicate also indirectly, maybe through the objects they are handling, and as in this case, we have two different robots handling an object, and they can communicate through the forces they are exerting on the object. So there is no direct communication. I'm doing this, I'm moving like that, but they take information about the other robot, what is doing the other robot, through the interaction, the physical interaction in this case. So we have physical and non-physical interaction between robots to coordinate. And then we have the space, because they live in the same space, they have to share this kind of resource. So as I was mentioned before, the collision avoidance aspects are important. And we can do that mainly for the collision avoidance aspects. We can work on different levels. So the high level, the task that assigned to the robots, ensure the safety of the system, for example. Okay? I just give you different tasks to different robots so that they will not collide. Or we can do that at lower levels, so, for example, a motion planning level or control level, so the robots have their own tasks, they decide the tasks that they have to do, and then they will move. And then while they will move, they will take care of the coordination, they will take care of the collision to be avoided. So we can do that at different levels, and we have different problems. Here we mainly have, like, here optimization problem, and here optimal control problems, to give more technical details. But we can solve them mainly if we have a high computational power, or we can distribute this decision through the single robots, for example, by rules. Okay, we coordinate following rules, and we can do that at this level and at this level, but also at this level. And we have rules that will ensure safety and will ensure also will provide some efficiency of the system. So we have different way of doing that. And here, for example, is an example of how to handle the task level. So we have robots that have to cooperate because the single object has to be positioned somewhere where a single robot cannot do that. Okay, so we need two robots to do this. So how do I assign tasks to single robots to accomplish a task that cannot be done by a single one. So that's an example, and just to, okay. I don't know if it was working, the movie? Okay, sorry. And this one is another task, just to show you that we also have to handle different robots. So we have a forklift that has to take a pallet and bring it to the manipulation system. And then we have a bimanual manipulation system where that it has to pick the objects from the pallet and position the object somewhere else. And also here we have to take care of the coordination of the robots that are different in this case. But the idea is to have a high-level planner so that we don't care that the robots are really different, and we are able to handle this anyway. I'm running out of time, and so just last one. This is the same situation as before, the same aero racing team, but it's competing with another car. This is Las Vegas this January, and this is the Tomb car, actually. And they are competing, so they are sharing the same environment. They don't want to collide, but they are competing on the time, so they have to also to win the race. So here again, we have multi-robot systems that have to cooperate, even though they have individual goals that are kind of opposite, right? They are competing. So we have to face also this kind of situation, not just in challenges, but also in the industrial environments where we have robots with different tasks. Cleaning the floor, deploying objects somewhere else. Okay, so just that was to give you the idea what we will have to face, so just not giving too many detail. But what I would like to do also is try to understand how we can teach robots to collaborate, because robots are not being designed to collaborate. So we learn how to collaborate in a high school, usually mainly, with other kids, and we learn to do that. How we can do that with robots? What does it mean, learn, understand the collaboration? So here is something that we are not yet there. We still have to face it, so it's something that we still have to work on. And with that, I thank you. If you have questions.
Thank you so much for the presentation. So we have some questions from the audience. Please raise your hand if you want to ask something. Okay, in the meantime, I can start. So you showed us different field of application of this system. What do you think will be the one where these technologies can have the biggest impact?
Okay, for sure is the logistics and the intralogistics in our industry, because they already use different robots, and they will have many more in the next future, but also in the huge spaces like airport, hospitals, we have seen different robots, but also for move medicines or food around the hospital, we already have robots doing that. So, and that's challenging because it's also crowded by humans. So that's another application area where we have to face this.
We have one question.
Yeah.
Yeah.
Thank you, Lucia, for the talk. I have a question regarding this multi-robot coordination task, where you said we shouldn't take inspiration from humans. So I'm wondering why not actually from humans or from biology in general.
No, I was joking. For biology, for sure. For well-behaved human, for sure. Not from Italian drivers. That was my only concern.
Why not? You can be, as Italian driver, you are very, very adaptive, you know,
right. What I'm always saying is that we will have very good robots, autonomous driving robots, when they will be able to drive in Rome and Naples. As soon as I see them in Naples and Rome, I see, okay, they are very good robots. No, I was joking, absolutely. Human inspiration and biological inspiration, as we mentioned before, it's useful also in this kind of system. It's kind of embodied intelligence that is not in the physical, but we have to embody that in them.
We have another question.
So you're currently doing robot-robot communication, and are you also planning to go into robot-humans communication, so you can include humans too in the whole swarm thing?
Yes, at the moment we are working with the robot-robot interaction, but there is also the human there, and it's not yet easy to understand how to communicate because the human is much more intelligent than the robot, and it's kind of unpredictable, while the robots are not. So it's something a little bit different that we have to take care of, absolutely.
All right, thank you.
One last question here in front.
From an earlier adaptation, is it always like looking at the robot-robot communication is the highlight, or, for example, do you also look at the design of the environment to make, for example, these robots interact with each other a bit easier? Design of environment, is it a concern, or do we always look at to keep the environment as it is?
At the moment, we have to keep the environment as it is because we are in the transient phase, right? So we are introducing robots in an environment that is already there. While when we are planning for new plants, then there we think the environment based on the robots that we will use. But it's something that is, I mean, it's completely different, and it's a huge investment to do something like that. So at the moment, we are just required to put more robots and more robots in an environment that is being designed for humans.
Okay, thank you so much again, Lucia. And I would like to conclude this session. Thanks again to all the speakers for the great presentation. Thanks for the audience for the active participation. Now we will have 15 minutes of coffee break, and then we will have the second session. The moderator will be Professor Ali Narboushaffer. So enjoy the coffee break, and thanks again.